Okay, so we'll pick up where we left off from last lecture. As we were setting up, we have a general framework for building Green's functions, and then corrections to those that account for boundary conditions. In a general boundary value problem, what we showed last time is that if LU is equal to F, X lives in U, which is a subset of Rn, BU is equal to G, for X is on the boundary here. Okay. Then in order to solve problems in general, the solution can be got by defining U equals V plus W, such that V is going to be a convolution of something we'll call a Green's function with F. Sorry, not necessarily a convolution, but an integration against it as a kernel. And W satisfies the homogeneous problem with the inhomogeneous boundary condition. Okay, and our Green's functions here are going to satisfy LGXY is equal to dx minus y, where x lives in U, y could be on the closure of U, and then the boundary condition acting on G should be 0, okay, on the boundary there. Okay. And importantly, this thing GXY, we can get this. It's equal to the fundamental solution minus this boundary correction term. The zero's at the boundary there. Okay, and so we have a PDE here for phi. Okay, what should this be? Okay, we'll talk about this shortly. Or sorry, what should the solution of that be? And then, right, its boundary condition. Not sure quite what I'm doing here. Needs to be matched to whatever the fundamental solution is at the boundary. Okay, so we're going to zero out the contributions of the fundamental solution there. We've actually done this before. We did this in the case of the heat equation when we just had the half line, solving the heat equation on the half line. We were able to zero out the boundary condition for the heat equation at x equals 0, essentially by just subtracting off a shifted version of the fundamental solution. And that, in general, is our approach for Green's functions, as we'll see in the case of the Laplacian. Okay, so let's make this concrete now by looking at Green's functions for our Laplacian. Okay, so in general, let's consider the Poisson equation. Okay, it's a Poisson equation, just minus Laplacian of U equals F, X lives in U. And then let's take a Dirichlet boundary condition, okay, which could be non-trivial. Okay, U is going to be open and bounded. Okay, du needs to at least be piecewise smooth, and we'll say that f and g need to be continuous, okay? Continuous functions. All right, fine, okay? So now we can already get some traction on this problem, right? Because we know that the Laplacian of u, right, on Rn has the fundamental solution given by phi of x, y, right, is equal to what? Well, it's going to be 1 over, and let me write this on the next page, right? Okay. I'll just jump ahead, right? So the fundamental solution given by phi of xy is equal to 1 over n minus 2 alpha of n here, right? Times 1 over x minus y to the n minus 2, so long as n is greater than or equal to 2, right? And then we also have a logarithmic function in the case of n equals 2, right? So the point is not necessarily the details of the solution, but that it's going to be non-zero in general on the boundary of u, right, for whenever u is a proper subset of Rn, okay? So what we do is we're going to define our Green's function as this fundamental solution with a function subtracted that's going to zero out our boundary. And that will allow us to solve that boundary value problem, okay? So this means that we need to solve the following PDE for little phi, right? It's going to be given by Laplacian of phi equals 0. And then little phi needs to equal, call it big phi of x, y, right? It is a function of x minus y, but let's keep this convention here, okay? So the PDE and the boundary term, right? So the point is that this needs to be harmonic on u, right? It has to be 0, right? So we can't have it become a delta distribution, right? And then for u being, some integral of the Green's function against f, right? Plus this correction term w, right? W of x is going to satisfy Laplacian of w equals 0 on our domain, and w is equal to g for x being on the boundary, okay? Now, how do we find little phi of x, right? Well, it turns out we can exploit the symmetry of our fundamental solution that will similarly be inherited by little phi, okay? So this basically comes from the phi of xy symmetry, right? Symmetry. Okay, if you look up here, right, at this formula, I can swap x and y, and it's the same formula, right? So we expect that, well, if that's true on the boundaries, right, we can also assume that we'll have similar symmetry of our function little phi of y, right? Because they're bound together, little phi and big phi. Okay. So